So in this video, we're going to focus on reactions of carboxylic acids. There's a couple of things that are worthy of noting, is that a carboxylic acid can only undergo nucleophilic acyl substitution in its acidic form. So the basic form, in other words, the carboxylate ion, like we talked about when we were doing the ester reactions, the negatively charged form, right, makes it resistant to nucleophilic attack. So can only react, or we're going to say they can only react via nucleophilic, just abbreviate that, acyl substitution in their acidic form. So the carboxylate ion cannot undergo nucleophilic acyl substitution. It is resistant to being attacked by a nucleophile because it's already a base, right? It's negatively charged. The other thing that's worth noting is that the carboxylic acids are nearly equal to esters in terms of reactivity. So these are close in reactivity. To esters. Because the leaving group, so it would be hydroxide for a carboxylic acid or an alkoxide if it was an ester, are similarly basic. Right, the pKa of water is 15.7. The pKa of an alcohol is around 15 or 16, something like that. So they're similar in basicity. So they have similar reactivity. The other thing that's worth noting is that we can get a carboxylic acid to react with an alcohol, just like we did an ester reacting with water, right? Hydrolyzing the ester to form the carboxylic acid and the alcohol. We can get the carboxylic acid, so I'm going to abbreviate this, RCO2H, will react with an alcohol. I'll just do ROH to make an ester. It's just the backwards reaction of the hydrolysis of the ester. Right, so all of those steps under acid catalyzed conditions were reversible. So the carboxylic acid and the alcohol were the products of that reaction. Those can react again and form your ester. So this is a specific type of reaction called a Fischer esterification. It's forming an ester from a carboxylic acid and an alcohol. It's acid catalyzed, usually done either at room temperature or under reflux, right? So sometimes if you've done one of these in your lab, you've probably set this up to reflux, or if they kept it easy, there's one where you can make the oil of wintergreen is a Fischer esterification reaction that can be just done in a test tube at room temperature. But essentially what you're going to do is take a carboxylic acid, and you're going to protonate it. So I'm just going to take H plus because we already went through this with the ester. You're going to encourage then that carbon to be attacked by the nucleophile. So we're going to protonate the oxygen of the carbonyl making the carbon hotter for nucleophilic attack. The nucleophile is going to be neutral, right? It's an alcohol, so it's not awesome. Like, it's not a negatively charged nucleophile. I'll just use methanol to keep it simple. So this is going to come in, attack the carbon. Remember, this carbon is sp2 hybridized, right? So this thing is trigonal planar. We're going to form our first tetrahedral intermediate. Remember the pattern that we said. Tetrahedral intermediate number 1, which is protonated, is going to look like this. So we have our hydroxyl group up here. We have another hydroxyl group over here. And we have our nucleophile, which still has its proton, or hydrogen, I should say at this point. So here you have tetrahedral intermediate number 1, which is positively charged. Since, again, all of these steps are reversible, we typically use the nucleophile, or in other words, the alcohol, in excess. So it's usually the solvent, right? Which means there's an excess of it hanging around. We can deprotonate our first tetrahedral intermediate to make our neutral tetrahedral intermediate. That's our intermediate number 2. Again, recognizing our pattern here. And you have acid laying around, right, in the flask. So we're going to, just like we did with the ester, and I'll abbreviate the acid just H+. It's probably pulling the proton off of the protonated methanol. And you'll end up with tetrahedral intermediate number 3, which is protonated. Right? So our tetrahedron is going to, or our tetrahedral intermediate, I should say, is going to collapse. We're going to kick off water. Again, all of these are equally able, so that the alkoxy group, the methoxy group, could have been protonated as well, just like I protonated the hydroxyl group because I chose to do that, right? But equal probability for either one to occur. Encouraging this reaction in the forward direction means we protonate the hydroxyl group and get rid of water, right? And form the ester. So in other words, keeping an excess of your nucleophile around, right, or an excess of one of your reactants around can help encourage the forward process by Le Chatelier's principle, because all of these steps are annoyingly reversible. So what you get, and I'll draw that suggestively because you know that's going to be plucked off, is your protonated ester. Water just took off, didn't it, in the last step? So it can come back and deprotonate the carbonyl, oxygen. What you get is the ester plus, we maybe didn't write this in the last mechanism, the hydrolysis of the ester, but you do get your acid catalyst back again. So this is your Fischer esterification reaction. In the lab, very often when we're doing this, we'll heat this up, but it doesn't always have to be heated up. It depends on how electrophilic your starting material is and how awesome your nucleophile is, right? So a lot of things under consideration with the reaction conditions. But since all of these steps are reversible, it helps to increase the concentration of one of your reactants. Once this thing reaches equilibrium and you've got more reactants, or you add more reactant, right? Or you have some excess available. So it's just swimming around, say, in the solvent that is also sort of playing double duty as the nucleophile. You will push the equilibrium to the right in favor of forming the product. So this is a reaction of a carboxylic acid with an alcohol to make an ester. We don't really see carboxylic acids undergoing nucleophilic acyl substitution with amines very often, and I'll show you why. So carboxylic acids don't often react with amines via nucleophilic acyl substitution. And the reason, we believe, is because the carboxylic acid is acidic. So the carboxylic acid is acidic, and an amine is a base. And so the acid will protonate the amine, and therefore you no longer have a nucleophile, right? I don't know what's going on with this paste thing that keeps popping up, and I'm not sure if you can see it, but so if you take away the lone pair of electrons on the nitrogen and have it become sort of involved in bonding, right? So you make an ammonium carboxylate salt, essentially. Let me show you. Then you don't have a nucleophile anymore because you've protonated it. So if I take an amine, like just say methylamine, just to keep it small and simple, then I'm going to, and let me put the lone pair of electrons on here, I'm going to protonate this using the carboxylic acid, and what you get is just an ammonium carboxylate salt. And that's just going to sit there and stare at you. So you're not really going to get a nucleophilic acyl substitution. If you want to make an amide, there are other ways to do it. But using a carboxylic acid isn't the brightest way, right? We saw in the video with the reactions with acyl chlorides, right? You can use one of those. You can use an acid anhydride. This is a good time to introduce one of those. But using just a carboxylic acid, probably not the brightest idea because you're just going to protonate your nucleophile and it's left non-nucleophilic after that, right? So no reaction's actually going to happen. You could lose a water molecule between two carboxylic acid molecules. So loss of a water molecule. This is essentially a great way to turn a carboxylic acid or two, so two equivalents of carboxylic acid, into a better electrophile, so make it more reactive by condensing them, essentially. So loss of a water molecule from two carboxylic acid molecules. So essentially condensing these two to spit out a water molecule will form an acid anhydride. So essentially anhydride means without water. And so these come from condensing two carboxylic acid molecules, ejecting one equivalent, or essentially 1 mole of water molecules. So these are actually often used more often than regular old carboxylic acids in the Fischer esterification process because they're more reactive. Their leaving group is better. So I'm going to draw these facing each other so you can see. We're going to take one of these and the hydrogen off of one of the other ones, and we're going to lose water. So you essentially cook these up, and what you get is the acid anhydride. The leaving group for this would be here. If I attacked one of those carbonyls, that would be the leaving group. So here's your leaving group. There's a carboxylate. And it's a relatively weak base. So in other words, pKa of sort of like a garden variety carboxylic acid is like roughly kind of like 5-ish. Remember, the lower the pKa, the stronger the acid, right? And the stronger the acid, the weaker its conjugate base. So, I mean, depending on what R is, right? The carboxylate anion is a relatively weak-ish base. So it's a pretty decent leaving group, which would, and it's definitely weaker than hydroxide. So instead of reacting the carboxylic acid, we could react the acid anhydride. And so we have set this up such that we have a better leaving group. The acid anhydrides do react with amines to give amides because there is no acidic hydrogen to protonate them. So, for example, we could take so you want to make an amide. You could use an acid anhydride in the first place instead of the carboxylic acid. So here I could take my amine, and since there is no acidic hydrogen now to ruin my nucleophile, I'm going to attack the carbonyl. You don't protonate this with any acid because, again, you don't want any acid in the pot. You would wreck your nucleophile. And what we're going to get here is a tetrahedral intermediate. This is always what happens. I'm going to draw all these out. Just put that there. The positive charge on the nitrogen. We're going to watch this tetrahedral intermediate collapse and kick off the weaker base. Still have both hydrogens on the nitrogen. We have kicked off the carboxylate anion. And these are in equilibrium with each other, right? So in other words, my amide usually you see the hydrogen just written underneath the nitrogen like that, plus the carboxylate, the ammonium carboxylate salt, and the amide is in equilibrium. With your protonated amide. So you can create, and we will do reactions with amides. So here's an amide. You can create an amide, and they are considered carboxylic acid derivatives because you can make them from carboxylic acids. But in this case, it is a little bit easier to turn the carboxylic acid into a more reactive group. And that is, or we should say, a less sort of self-sabotaging group, right? By creating the acid anhydride, which does not have acidic hydrogens, or I should say, it doesn't have hydrogens that are acidic enough to protonate your amine and wreck your nucleophile. So you can then attack. So this is kind of like a carboxylic acid in disguise, these acid anhydrides. They're pretty reactive, so usually you keep them under argon or under nitrogen in either the fridge or the freezer, because if you let water get near these, you'll crack them open and you'll just have two carboxylic acids staring at you. So in the next video, what I'd like to do is show you reactions of amides and also introduce another piece of functionality called a nitrile. I'm going to save that for the amide video. So we have two new functional groups here that are sort of derivatives of carboxylic acids. A nitrile is going to look like a derivative of an amine. So I want to introduce you to those.